Topics in post-harvest technology: control of ethylene, external sources of ethylene. All higher plants produce ethylene, but in very small amounts. Ethylene can also come from a number of external sources, such as burning rubber, kerosene burners, propane forklifts, especially if they're not properly maintained, decaying wood, decaying produce, though in most cases the majority of that ethylene is being produced by the mold that is decaying the produce, not by the produce itself, and cigarette smoke. Ripening fruits such as apples, bananas, pears, and tomatoes can produce appreciable amounts of ethylene. So, what are some methods to reduce ethylene in storage or during shipping? We can use potassium permanganate, KMnO4, a powerful oxidizer. The potassium permanganate destroys ethylene, but in the process, it is also consumed, so it must be replenished. One of the most famous trade names for formulations of potassium permanganate is Purafil. Historically, sachets containing Purafil were placed with kiwi fruit shipped from New Zealand to prevent the fruit from prematurely ripening. We can use activated charcoal. A system can be set up so that our storage air passes through an activated charcoal bed where the ethylene is adsorbed to the charcoal. When the bed becomes saturated, by using a series of valves, we can flush the bed with outside air to purge the charcoal bed of the ethylene. This rejuvenates the charcoal, and switching the valves again, we can reintroduce storage air through the adsorbent bed. Ultraviolet scrubbers have been developed to remove ethylene. The scrubbers use electricity to produce high-energy ultraviolet light that creates ozone as the UV reacts with the oxygen in air. Ozone is a very strong oxidizer. When the ozone encounters ethylene, the ethylene is destroyed. There are catalytic oxidizers. Storage air is introduced to the unit where it flows across a heated catalytic bed or through a tube containing heated catalyst. Ethylene contacting the catalyst is destroyed. There are also palladium-embedded zeolite films. This is a relatively new technology. Zeolites are minerals that have a pretty good hydrocarbon absorbing capability. By adding palladium, a heavy metal, we can make them much more effective in absorbing ethylene from the environment. If we embed these zeolites in films and then, for example, seal produce trays with the film can absorb ambient ethylene or ethylene produced by the product itself. Ventilation is probably one of the simplest methods, but it is very effective. Here in California on the Central Coast, we tend to have cool nights year-round. Vents in storage facilities can be opened to admit cool outside night air. This air is used to purge the storage area, reducing ethylene levels. Since the purge air is cool, it doesn't heat the storage area much, and minimal energy is then needed to recool the storage area to its original temperature once the purge is complete. You want to store your product at the lowest safe temperature of storage. This will limit ethylene production as ethylene production is lower at low temperatures. Also, significantly, ethylene action is lower at low temperatures. So even when you have ethylene in the air, if the temperature is low enough, that ethylene will not be very effective in creating a response in your product. You should avoid storing damaged or bruised fruits, vegetables, and flowers with undamaged product. Ethylene is produced as part of the healing response in plant tissues. When you have damaged product, that is, when it's bruised, lacerated, or abrased, the tissues will attempt to heal. They will start producing ethylene, which will cause a rise in respiration due to the mobilization and utilization of the cellular components involved in the healing process. If you can minimize damage to your commodity, then your concerns for ethylene and its effects in the storage environment go way down. It takes 1 to 3 days for wound respiration to subside. You can elevate ambient CO2. The reason this is effective is because it's a competitive inhibitor of ethylene. Ethylene, when it's produced by plant tissues, migrates to a receptor where it combines with the receptor, and this then starts a chain reaction which causes changes in the plant cells. CO2 fits into that receptor and prevents ethylene from joining with it, so the ethylene can't then elicit a change. Decreasing ambient oxygen can also be effective, as oxygen is absolutely needed to produce ethylene. Here is the biosynthetic pathway for ethylene production. Methionine is an amino acid present in plant tissues. It is enzymatically converted to a compound called S-adenosylmethionine, or SAM. The SAM then is enzymatically converted into the compound 1-aminocyclopropane 1-carboxylic acid, or ACC. The ACC is subsequently enzymatically converted into ethylene. Notice where SAM is being converted to ACC, forms of stress will promote the formation of ACC. Those stresses include wounding, chilling injury, drought, and flooding. Where ACC is being converted to ethylene, there are some factors that can inhibit this process, with the most notable factor being low oxygen. You can utilize modified atmosphere packaging to help control ethylene and its effects. Modified atmosphere packaging refers to packaging that will change the atmospheric composition around your product. This can be a lower oxygen level than normally found in air, a higher CO2 level than normally found in air, or higher or lower relative humidity. The ambient oxygen level on average is 20.9%. The ambient CO2 level on average is 0.41%. So if you alter the level of either or both of these gases, you will have a modified atmosphere. With lower oxygen and higher CO2, there will be both less ethylene produced, and what is produced will be less effective on plant tissues. Modified, however, implies that it is non-precise. For example, you put your commodity in a film bag and you let the respiration rate of that product reduce the oxygen and increase the CO2 in the bag. Since plant respiration is temperature dependent, the final levels of oxygen and CO2 that will develop in the bag are dependent on the storage or holding temperature. If that temperature is changed, then the levels of gases in the bag will also change. You could store your produce in controlled atmosphere, or CA storage, to control the production and effects of ethylene. Notice the word controlled. This is a precise method of storage, but it's limited in its applicability. We really don't use this method for most vegetables. It's primarily used with fruits that have the potential to store well, or which are high enough in value to justify the cost of CA storage. Examples of fruit stored in CA are apples, pears, and cherries. Under normal conditions, if you pick good quality apples and put them into refrigerated storage, you can expect 4 to 6 months of storage with those apples. With CA storage, we lower the oxygen to a precise level and keep it there. We raise the CO2 to a precise level and keep it there as well. The precise levels depend on the apple variety and area of production. By doing this, the storage life can be extended to 12 to 13 months in many cases, and since we're using low oxygen and high CO2, both ethylene production and action are greatly reduced, and the fruit can come out of storage without having ripened. We can use hyperbaric storage. Hypo means below, and baric refers to atmosphere. So it's literally below atmosphere storage or low pressure storage. It's been investigated for a number of products, but its commercial use in the United States has been very limited. With hyperbaric storage, product is being held in a vacuum. Not a full vacuum, but a moderate to low vacuum, so it requires specially reinforced storage facilities so that they don't implode. The idea here is that under low pressure, the driving force for ethylene to escape tissues will be increased, plus under low atmospheric conditions, Oxygen concentration is going to be low, which will reduce both the respiration rate and rate of ethylene production from the product. You want to rapidly cool your commodities after harvest to reduce respiration rate and the rate of ethylene production. You want to maintain high relative humidity in storage to reduce water loss. Water loss, if it's excessive, is a form of stress, and stress will promote ethylene production. You want to stack crates and boxes to allow uniform airflow within the stacks and between the pallets. If there isn't uniform airflow within the stacks and between the pallets, hotspots can develop due to product respiration. Higher respiration equates to greater heat production, which will in turn promote even higher respiration. This will lead to a decrease in shelf life of the reheating product and increased levels of decay. You want to use electric forklifts. Electric forklifts have no emissions, so ethylene isn't a consideration. You want to keep your packing houses and storage facilities clean to minimize contamination and subsequent rot. Remember, rotting produce can produce ethylene, so having a clean facility is going to eliminate not only decay organisms, but a potential source of ethylene. You want to avoid mixed loads and mixed storage. Do not combine tomatoes with lettuce, bananas with ethylene-sensitive flowers, tomatoes with cabbage, or apples with kiwi fruit. The tomatoes, bananas, and apples are ethylene producers and can produce appreciable amounts of ethylene. Lettuce is sensitive to ethylene and can develop russet spots. Cabbage leaves can turn yellow. Kiwi fruit is very, very sensitive to ethylene at the parts per billion level, and with exposure will prematurely ripen and excessively soften. So you need to avoid then storing or shipping ethylene producers with ethylene susceptible commodities. What are some chemical treatments to prevent ethylene action or its formation? Silver thiosulfate, or STS, has been used for many years in the floral industry. Stems are placed in an aqueous solution containing the STS, and the silver thiosulfate moves fairly rapidly in the plant tissues, where it dissociates to release a silver ion. The silver ion combines irreversibly with ethylene's receptor, preventing ethylene from binding to the receptor, so no changes can be initiated. The silver has no effect on the plant tissues other than to block ethylene. Since it binds irreversibly to the receptor, STS is known as a non-competitive inhibitor of ethylene action. Silver thiosulfate use has decreased dramatically in recent years as silver is a heavy metal, so disposal of unused solution is difficult. The solution is considered hazardous waste. Also, silver has increased dramatically in price in recent years, making use of this chemical much more costly. Lastly, a non-toxic alternative to silver thiosulfate is now available. A relatively new, non-toxic alternative to STS, or silver thiosulfate, is 1-methylcyclopropene, or 1-MCP. It is applied as a fumigant rather than in aqueous solution. It is marketed in the U.S. under two trade names, Ethylblock and SmartFresh. Ethylblock is used with flowers only. SmartFresh is used with select fruits and vegetables. Here is the formula for 1-MCP. Like silver, it combines irreversibly with the ethylene receptor in plant tissues. After application, excess 1-MCP can be vented to the air as it is not toxic to humans. It has been widely adopted for use by florists as well as by fruit growers. SmartFresh is labeled for select fruits and vegetables. Notice this list of fruits as well as some vegetables like broccoli and tomatoes. Two chemicals that are also used in the industry to limit ethylene are amino oxyacetic acid, or AOA, and aminoethoxyvinyl glycine, or AVG. Both reduce ethylene production from treated product by inhibiting the conversion of S-adenosylmethionine, or SAM, to 1-aminocyclopropane 1-carboxylic acid, or ACC. Both AOA and AVG inhibit the action of the enzyme ACC synthase. Summary points. Ethylene is produced in large quantities by some fruit, but can also be produced by propane forklifts, decaying produce, and wood. Potassium permanganate is used to reduce ethylene in storage and during produce and flour shipment. Additional methods to reduce ethylene in storage include using UV ozone generators, catalytic oxidizers, and ventilation. High CO2 and or low oxygen reduce ethylene effects and production, respectively. Silver thiosulfate is used to greatly reduce ethylene effects on flours. 1-MCP, a widely used fumigant, greatly decreases ethylene effects on fruits, vegetables, and flours. Avoid storing and shipping ethylene-generating produce with ethylene-sensitive produce.